Hello, good morning, and hello again from the EuroVis conference. My name is Gerrit Scheuermann, and I'm the session chair for the session. As you can see, full paper 7 medical applications and GPUs. We have 3 very nice applications that show you the variety of modern applications in visualization. It ranges from improvements of GPU programming that most of you probably do themselves, over tracking more efficiently the movement of proteins in biological cells, all the way to supporting the FDA, the Federal Food and Drug Association, in processing medical incidents. Of course, the presentations will give you all this information in more detail. Our first speaker is Yifan. He is from the William and Mary College, and he cooperates with Yixuan Zhang, Ali Mosallaei, Michael D. Shah, Cody June, and David Kaeli. They are from the Georgia Institute of Technology, Lexington High School, and Northeastern University. So it's a broad cooperation, as you expect from an application. And Yifan, the stage is yours. Give us your nice talk on how to support all of us in our GPU endeavors.
In the spring of 2019, a group of researchers from Northeastern University was trying to improve a GPU hardware design to train machine learning models faster. GPUs, or graphics processing units, are initially designed for rendering three-dimensional scenes for gaming, architecture design, product design, and animation movie making. Nowadays, because GPUs are running so fast, people also use GPUs for scientific computing and artificial intelligence. Hardware designing is typically a very time-consuming process. Researchers need to iterate on their design to achieve good performance. However, as the researchers from Northeastern University input their first design into a GPU simulator, their design runs 10 to 20 times faster than highly optimized commercial GPU. Rather than feeling excited, they are confused. Can there be a problem in their implementation, or is there a problem with the GPU simulator? Unfortunately, they have no easy answer to the question. The GPU simulator provides high-level performance metrics, such as the time required to execute a program. These high-level performance metrics are too general to infer what exactly is happening in a GPU. A GPU simulator can also provide low-level traces that records every event that happens in a GPU hardware component. However, simulating 1 second of a GPU execution can produce terabytes of traces. It is almost impractical to read the traces without facilitating tools. This is not the only case that shows the difficulty in understanding hardware performance. We have conducted a survey with 37 hardware designers, where participants are given a list of statements and are required to select from strongly disagree to strongly agree on a 5-point scale. We also ask a few open-ended questions to understand their performance analysis workflow. From the survey, we observed that the hardware designers lack confidence in making sense of the performance changes, spotting performance bottlenecks, and finding evidence. 56% of the participants use guessing as a strategy to identify the performance issues and lack systematic performance analysis solutions. Our participants also express their need for tools that can help them understand the performance metrics and visualization tools that visualize the simulator-generated execution traces. Visualization is one of the best solutions that can reveal the patterns behind the huge amount of data. While there are many visualization tools that are designed for performance analysis, they cannot really solve the problem of hardware designing. For example, this is a screenshot used in the Chrome browser development tool. The most important part is based on the icicle plot. It is essentially a Gantt plot with each box representing the execution of one function. It also reveals which function calls which other function and how long each internal function takes to execute. This is very useful for analyzing software performance issues. However, as the concept of function is only in software and is not used by hardware. Most software-oriented performance visualization tools are not useful for hardware performance analysis. So what is unique about hardware visualization, and especially GPU execution visualization? To understand this question, we need to dive deeper into how a GPU works. A GPU works under the supervision of a CPU. The CPU sends commands to the GPU to execute. These commands can be memory copy commands which transfer data between the CPU and the GPU. The commands also include kernel launching commands. A kernel is a program to execute on a GPU. A kernel launching command instructs the GPU to start the program execution. In GPU programming, a kernel can be divided into a list of workgroups. Each workgroup can be further divided into a list of wavefronts. Each wavefront contains a certain number of work items. Each work item is like a CPU thread. They execute the same program but process different data. We call the collection of work items in a kernel a grid. The GPU has a command processor to process the command from the CPU. For kernel launching commands, the CPU sends the grid to the command processor. The command processor breaks down the kernel into workgroups and sends the workgroups to the compute unit in the GPU. A compute unit is like a core of a CPU. It is where the calculation happens. A compute unit contains several wavefront pools that can hold dispatched wavefronts. A scheduler in the compute unit can send the wavefronts to the SIMD unit to execute. The SIMD unit contains the calculation circuit and can calculate 16 operations in a fraction of a nanosecond. A typical GPU can contain 64 compute units, and the compute unit contains 4 SIMD units. That means a GPU can calculate more than 4,000 operations in a fraction of a nanosecond. In a second, a GPU can calculate thousands of trillions of instructions. The large number of parallel components and the parallel operations creates a severe challenge to designing visualization tools for GPUs. We need to reveal the complex behavior of all the components at a level of detail that is smaller than a nanosecond. This is only what happens in a compute unit. The memory subsystem may create a more chaotic behavior pattern. The data that the GPU needs to process are stored in the GPU's main memory. The compute unit needs to fetch the data from the main memory using the memory controller. But the GPU main memory is too slow to supply the data to compute unit. To boost the memory transfer speed, GPUs are equipped with multiple layers of caches. When the compute units share and compete for the data in the caches, the behaviors are extremely complex. The visualization tool has to show the behavior of each component and allow the designers to design how the components interact. Now, we see why the computer architecture community requires a specialized tools that can help them understand the detailed behavior of hardware execution. The next question is how the tool is supposed to work. How can the tool facilitate humans understand hardware behaviors? We start by understanding the current workflow of hardware designers. We interviewed 5 designers and used the hierarchical task analysis to formalize the process. The overall goal of a researcher is to propose new hardware designs that improve hardware performance. At a high level, improving hardware performance requires evaluating the performance of the current design, identifying the performance bottlenecks in the current design, and propose new designs. After having a new design, the new design becomes the current design, and the performance needs to be evaluated again until the design goal is achieved. To evaluate the performance of the current design, a designer models the hardware implementation in a simulator and collects the performance metrics and traces. Using the metric and traces, designers can start working on identifying the performance bottlenecks. According to our interview, we find the designers usually start with finding the workload of each component. They try to find which component is working under stress and which component is not given enough tasks. Those designers, as domain experts, know which component they want to check. Therefore, they need to filter the component from a large number of components in the system. For different components, they also need to select different metrics that can best represent the working condition. Finally, they usually have ideal numbers of metrics in their mind. They compare the achieved metrics with the ideal matrix to determine if a component is underloaded or overloaded. The next step, after identifying the overloaded or underloaded component, is to understand why a component is underloaded or overloaded. We find that the designers take two solutions. First, they compare the directly connected component to see if the upper component is assigning enough tasks or if the lower level component is handling tasks fast enough. For example, if a cache module is not doing enough work, a designer can check if the connecting compute unit is sending enough requests to the cache module. Second, designers also check parallel component to see if there is any load imbalance problem. Finally, we observed that hardware designers rarely make decisions using a single matrix provided by the simulator. They seek more details to justify and verify their assumptions about the cause of the performance issues. Ideally, hardware designers want to see what the problematic component is doing. They need a fundamental understanding of the problem before they can confidently reason about the performance issues. After the reasoning process, designers propose new designs, which is out of the scope of this work. But after a new design is proposed, they need to evaluate their design again on the simulator by collecting metrics and traces. Moreover, in this time, they need to compare the performance with the previous design and check if the performance bottleneck is resolved and the design goal is reached. Typically, hardware designers need to repeat the process many times before they can find a satisfying design. Using the knowledge learned from the task analysis, we then design Daisen, the visualization framework. Daisen first provides a data collection library that can build into a hardware simulator. As we integrate the tool with mGPUSim, a GPU simulator, a user can simply add -trace-viz command to collect data in a MySQL database. After finishing the data collection, a user can start the visualization tool as a server, and multiple users can use the web-based visualization interface simultaneously. When a user types the URL in a browser, the user first sees the overview panel. We use small multiples to show how performance metrics change over time in each digital circuit component. We show the name of the component on the top left corner and also show a figure below the title. The x-axis of the figure is the time in the execution, and there are two curves in each figure. Users can select what metrics they want to visualize with each curve. They can also turn off one curve by unselecting a metric in the drop-down menu. The metrics provided by Daisen are general and can carry rich information. For example, using the buffer pressure metric, we can see that there are a large number of requests waiting in the buffer of the L1 cache. By using the metric called the number of concurrent tasks, we can see that the utilization of this SIMD unit is only 15%, which is under the design value. Since there's a large number of components in a GPU, we allow users to switch between pages to browse all the components. Users can also use the filter box to directly jump to the components with certain names. In addition, users may want to make customized combination of components. They can achieve this by using a special syntax to make any combination. By default, each widget shows the duration of the whole simulation. Users can zoom in and out with mouse wheels and move the x-axis by dragging. When one widget updates the x-axis, all other widgets follow. These features create an alignment effect so that users can easily compare the metrics of different components. Overall, the overview panel enables users to find which component causes performance issues at a certain time. But how do they know what is the root cause of the issue? For example, we see this cache is not processing enough requests, since the buffer pressure is way below 1. How can we know what the cause is? To have a deeper understanding of the execution, a user can click on the name of the component. Daisen switches to another layout that includes a task view, a component view, and a legend on the right side. The component view shows all the tasks that are executing in the component hierarchically. For example, here, we see this component is processing a read request, and internally, it's processing another request that has a category of L1 transaction. Furthermore, To process the L1 transaction, the L1 cache initiates another memory read task, which is a request sent to an L2 cache. We see that there are big gaps between the tasks in this L1 cache, suggesting that the L1 has low utilization. We need to check why the L1 cache cannot receive enough requests. To check where the tasks come from, we first need to click on the task to enable the task view. The task view shows the task we just clicked as the current task. We can also see the parent task and the subtasks of the current task. As we click on the parent task becomes the current task, and we can navigate up in the task hierarchy by keep clicking on the parent task. The component view always shows the component where the current task is executed. As we move up the task hierarchy, we see that we moved to a component that is called address translator, and the tasks here are still sparsely executed. And as we keep going up the task hierarchy, we finally arrive at the compute unit, where the instructions are executed. We can identify the instructions that issues the memory request. The key information we need to check is what the compute unit is doing right before executing the memory instruction. To first have an overview of what is executing in the compute unit, we can hover on the legend items to locate all the tasks of a certain type. We see all the big rectangles are workgroups. Each workgroup owns one wavefront, and each wavefront executes many instructions. The instructions that takes the longest time are the vector memory instructions. Some other instructions take shorter times, including VLU instructions and scalar instructions. Right before that instruction, we see that only a few wavefronts are executing. When we start the instruction, all other wavefronts are working on VLU or scalar instructions and do not have memory requests to the memory system. Here the compute unit is only executing 3 to 5 wavefronts. Considering that a compute unit can run up to 40 wavefronts in parallel, the performance issue comes from the fact that the command processor is not sending workgroups fast enough to keep the compute unit busy. After finding this performance issue, a GPU hardware designer can try to improve the command processor dispatching speed. Here, we change the parameter in the simulator, and we visualize the GPU execution again. Here, we change the parameter in the simulator, and we visualize the GPU execution again. As a comparison, we can see the execution time is reduced from 55 microseconds to 44 microseconds. As we compare the component view of a compute unit, we can see that on the 6th row, there are more workgroups, suggesting the compute unit can run more wavefronts at the same time. So far, we have used a real-world case study to walk you through how to use the Daisen visualization tool. To evaluate Daisen, we conducted interviews with 10 hardware designers. At the beginning of each interview, we showed them the example you have just watched in this video to inform the participants about how to use Daisen. Then, we showed the participants a similar example. We asked the participants to find out the performance bottlenecks in that particular example and asked them to give suggestions about how to alter the hardware design to improve the performance. Finally, before the interview ends, we asked general questions about their feelings about Daisen and asked them to fill in a post-study survey. Each interview lasted about 90 minutes. Overall, our participants give very positive feedback on Daisen. 9 out of 10 participants successfully identified the performance bottlenecks of the given example, and 7 of them can give effective performance improvement suggestions. The post-study survey is also overwhelmingly positive. Our participants can use Daisen to understand the workload characteristics, identify performance issues, locate overloaded hardware components, identify hardware components execution trends, examine software factors that causes bottlenecks, identify opportunities to improve performance, and validate the design by comparing against the baseline. Overall, we see that the design of Daisen can fulfill its design requirements and can serve as a handy tool that helps hardware designers analyze performance issues. In conclusion, in this work, we surveyed and analyzed the requirement and the workflow of hardware designers on performance analysis. To meet the requirement of hardware designers, we designed Daisen. Daisen is a universal visualization tool for hardware designers to inspect extremely low-level execution details. It is effective in identifying performance issues and verifying the performance improvement of a new hardware design. As of today, Daisen has already been used to facilitate hardware designs and research in solving real-world problems. Daisen is delivered as open source software. If you like it, please feel free to give it a try.
Okay, hello again. This is Garrick, the session chair. You can see me on the left. I encourage everyone to post questions in Discord. We have a nice student volunteer in the back that poses those questions to me, and I will forward them to Yifan. To get a bit started, Yifan, I thank you very much for an application that probably concerns work that at least half of the audience have done before. So one of the questions I have is, what do you have to change if you would like to apply this to a different GPU architecture? Not completely different, but let's say some other hardware where you have more or less wavefronts, processing units, and so on. Is that a lot of work? Is it just a little bit?
Okay, so the question is what we need to change if we want to adapt the visualization to another GPU. So the first question is this another GPU can be a very different GPU. Like if we currently support AMD GPUs, then if you want to change to another AMD GPU, it's more simulator development work. It's not a visualization tool development work. So we actually want to try to keep it very straightforward, very easy, and very general. You can see all the metrics that we're using and all those we abstract everything as tasks. So it's very general. So there's nothing specific to GPU. There's nothing specific to this particular GPU. So we have instrumented this particular GPU simulator so that you can generate this type of or format in traces. But if you want to change some parameters, you can change the configuration in the simulator. Then you generate another trace, you visualize another trace. So almost you use it again, there's no overhead. But if you want to simulate a totally different GPU, you probably need to develop a new simulator. But we provide a very straightforward library so that you can instrument your simulator. So, for example, just one example, the L1 cache, the GPU cache. Then the original cache probably implemented in 3,000 lines of code in the simulator. Then we added around 10 to 15 lines of code to instrument it, just to mark where the transaction start, where the transaction ends. Then all those, say, buffer pressure, like number of requests that can be handled by this L1 cache are automatically generated from the traces that we collect.
Okay, that sounds good. Once again, I encourage everyone to post questions to Yifan. Yeah, of course, you can continue, but right now, I'm asking you really for questions. But by the way, you have this, and I said that before, very nice applications where half of the audience can talk about themselves because they know this application. We are not just the visualization people here. We're also on the application user side. So one obvious question is, have you tried it yourself? Did you analyze one of your own GPU programs by your own Daisen system?
So actually, we do use it. I use it a lot. So first of all, I I am a GPU architect. I work on computer architectures. I do not have I actually other publication in the visualization domain. So at the beginning, we encounter this problem, say there's something happening in the simulator, but we don't know what is happening. So we develop these tools. Then we actually use it every day, then mainly to understand what is going on in our simulator. Is it the simulator implemented? So that's for daily uses. We actually use this quite often to understand what's going on. And there's some very convenient features like sharing URL so that others can see exactly the same thing as what I can see. It's also actually very, very useful that I use it to communicate with others, to show what is going on. So it's a good education tool for others.
Okay, thank you. There's a question by Robin Mack. What is your biggest advantage over other GPU code debugger like NVIDIA Insight? Yeah, you're probably familiar with this system as you are an expert, not only on AMD GPUs. So what's your take on that?
Yeah, so the NVIDIA Insight is a commercial tool. So it's designed for a different goal. If you have used the NVIDIA Insight or NVIDIA Visual Profiler, they provide something very similar to a regular profiler that you can show those Gantt charts, like where a function starts, where a function ends. But it generally is actually at a very high level. It shows millisecond level granularity. But what we want to know is what happens in every nanosecond. And a very each transaction in the L1 cache, each instruction, how long time each instruction takes. So the granularity is very different, and the thing that we want to visualize is very different. So that's why it's somehow related. Like at a glance, you may feel it's pretty much the same thing as a NVIDIA Insight, but actually it's visualizing very different things. So they have API calls, so they have function calls, they have this function calls another function, this hierarchical relationship. But what we want to do is we want to visualize instructions and cache access. So we do not have this type of function concept. So again, we are implementing very different things. We're visualizing very different things from these publicly available NVIDIA and also AMD profilers and debuggers.
Yeah, thank you. Once again, to remind the audience, if you're not so familiar with small fractions of seconds, there is 1 million nanoseconds within a millisecond. So it's a factor of 1 million to just give you an idea of how much deeper and more fine granularity Yifan is actually looking at. Yeah, so can you probably to end this, give us a small example where you figured something out with your Daisen system that helped you to understand some bottleneck in your program or so?
Some example that I find. So for example, one thing that I find is that I find, when a GPU want to access the memory, it actually holds a virtual address. It needs to translate this physical address. It needs to translate to physical address before accessing the cache, the memory. So we realize in some benchmark, this translation is a global bottleneck. It takes like 30% of time, and it's actually not doing any actual work. So that is what we can clearly visualize the percentage between real memory access and the address translation process. We see some application is fine. The translation is very fast. Some translation is super slow.
Okay. Yeah, no, that's something we can all understand. Looking at the time, I guess we are ready to refer to the next speaker, We all thank Yifan for the very nice presentation, also for the nice explanations. And if you have missed it on the slides, he welcomes everybody to test this. And he is around, of course, on Discord. You can continue to discuss this very nice work there. Of course, you're welcome to read his paper or post questions directly to Yifan. I guess he's around, and you could see from the talk and the explanations in the questions that he's really an expert, probably close to a nerd who's really deep into GPUs. So take your chances on him, and thank you once again for a very nice presentation. Of course, this continues to all of your co-workers.
Thank you very much for the questions and your introduction. So one advertisement is that I am currently the assistant professor at the College of Mary, and I'm hiring PhD student. So if you have any PhD student who want to work on visualizing any hardware behavior, then please feel free to reach out to me. Thank you very much.
Thank you. Okay, once again, hello from the medical applications and GPU session. We are slightly turning now towards medical applications. The next presenter, Torin McDonald from the Ski Institute at Utah, with his co-worker, Shrestha, Xiyu, Bhatia, Chen, Goswami, Pascucci, Turbyville, and Bremer. They are partly from the Ski Institute, partly from Lawrence Livermore, and they work closely together with the Frederick National Laboratory for Cancer Research. And this gives you a hint. We're looking at leveraging topological events and tracking graphs for understanding particle diffusion. And you will see this is about the movement of specific proteins in cells that are probably, especially their movement and clustering, is responsible for signaling cancer events. More details will be given by Torin in his nice presentation coming up now. Thanks a lot, and listen to it. And once again, you are encouraged to post questions in Discord. You can already do that during the talk, because you're not going to interfere with Torin if you do that in the Discord channel, of course. Thank you, and Torin, it's all yours.
Hi, my name is Torin. I will be presenting leveraging topological events and tracking graphs for understanding particle diffusion. This work was performed in conjunction with the Scientific Computing and Imaging Institute at the University of Utah, the Frederick National Lab for Cancer Research, and Lawrence Livermore National Lab. Our work is in the application of domain of single particle tracking, which is a crucial tool in a range of biological applications. What you see on the top right is a series of frames taken from a movie of proteins moving around in a lipid bilayer. These movies are created using high-resolution fluorescent microscopes, and each of the dots you see moving around is a protein that has been fluorescently tagged in order to observe it through the microscope. One of the main focuses in SPT analysis is to quantify the kinetics and behavior of the particles, and one of the most common forms of analysis is quantifying how these particles diffuse. There are a number of steps to get to this point: data acquisition, segmenting the data, which is identifying which of these dots is a protein, tracking, which involves linking the segmented proteins across frames, and analyzing the resulting particle tracks. The first three steps have been widely researched in this domain, and our work is focused on the analysis of the resulting tracks. There are a number of limitations in these SPT datasets. For example, only 5% of proteins are tagged. These proteins can jump on and off the membrane, and due to low resolution and noisy nature of these datasets, the ability to distinguish clusters of particles and the number of particles that may exist in these clusters is lacking. This bottleneck implies that particle motion is widely analyzed without knowing the true count of particles in the observed tracks, which poses significant challenges in the scientific interpretation of the data and limits the insights that can be delivered through the analysis. Traditional analysis may produce something like this gray plot, where the diffusion is produced by using all the tracks, but without knowing whether specific tracks are associated with clusters of particles. Our goal in this work is to come up with a solution to mitigate this bottleneck by inferring a lower bound on the count of the number of particles that exist within a cluster in order to enhance the information a plot like this gives. Instead of a single plot, our technique can produce distributions for tracks that have an inferred cluster size. So in this work, our collaborators at FNL are specifically interested in the KRAS4B protein, and I want to spend just a couple of minutes talking about the biology because it's really quite fascinating. KRAS4B is a protein that modulates the signaling pathway for cell growth. Approximately 19% of patients with cancer harbor RAS mutations. Consequently, there is significant interest in understanding the underlying biological mechanisms of KRAS4B in hopes of developing effective treatments. However, despite decades of efforts, such as the RAS Initiative of the National Cancer Institute, it has proven challenging to find effective inhibitors of KRAS to the extent where until recently has been often labeled undruggable. As an alternative, the community is spending significant attention into better understanding the entire signaling cascade in hopes of finding ways to affect KRAS indirectly. Importantly, there is a hypothesis that the clustering of KRAS proteins drives downstream signaling events. However, since the biological significance of nanoclustering is not clear, it is important to clarify the dynamics of the behavior and understand the precise mechanism of assembly. This is what our work is focused on. To study these proteins, biologists conduct a series of experiments that are designed to test how the protein's behavior is affected by different membrane compositions. These experiments produce multiple movies, each containing 5,000 time steps. Once the segmentation and tracking steps are performed, the resulting tracks are used to produce diffusion analysis. The backbone of our work for analyzing the dynamic of these proteins is a tracking graph. Tracking graphs are a visualization tool that are used to help understand the correlations between features across time. Thinking about the dataset we have on the top right, the goal of tracking graphs is to give a visual representation of how each of the bright white dots are connected across frames. The bottom figure shows part of a tracking graph. The x-axis represents time. Nodes represent the segmented features in a time step and are aligned on the y-axis. The edges between nodes represent the correlations between the features across time. For example, these correlations may be features within a certain radius of a specific feature at future time steps. Tracking graphs have been studied in the visualization community in multiple application domains, and if you're interested after this talk in learning more about them, I'll refer you to the visualization contest from the 2016 Viz conference. One of the first things we noticed is that for specific lipid bilayer compounds, we see the occurrence of merge and split events within the tracking graph structure. It's important to note that the traditional SPT analysis ignores these events, and for doing diffusion analysis, tracks that contain these events are broken into individual segments. Our work uses these merge and split events in the tracking graph structure to infer a lower bound on the count of particles within a cluster. Using this technique, we provide more in-depth insight into the data than traditional SPT analysis techniques. We integrate this method into an open source visualization tool for analyzing SPT data. This figure shows the data flow of this system, and I'm going to talk about the three main components of this system, focusing on a new algorithm for SPT analysis and the visualization tool we developed for exploring and analyzing SPT datasets. The first problem we approached is how to define features that exist across multiple frames, and also defining these time-varying features across merge and split events. For the rest of this talk, I'll refer to features as a representation of the segmentation at each individual time step, and time-varying features as a set of features that are linked together across time. TVFs are defined by a set of properties. These include a birth and death time, which represent the time steps at which the TVF appears and disappears. Correlated features, which represent all the associated individual features for the TVF over every frame in the TVF's lifetime, and links to other TVFs that are connected to the current TVF via merge and split events. To construct TVFs from the tracking graph, we iterate through all features in consecutive time steps. There exist two scenarios where a new TVF is created. One, if the current feature of interest has no backward edges, or two, exists directly after a split or merge event. Similarly, a TVF dies when either the current feature has no forward edges or is the node at which the merge or split event occurs. Every TVF that is either born or after a merge or split event, or dies at a merge or split event will contain a link to the corresponding TVFs that are connected at these events. By doing this, we can easily link these features across merge and split events. Importantly, we also maintain the most correlated link between features as defined by this cost function, which combines the distance between two features and the ratio of intensity between the two features. So if we have this split event on the bottom here, we can compare each of the features using the cost function, and if the bottom set has the lowest cost, we'll mark this edge as the most correlated link. So computationally, merge and split events are observed through the tracking graph structure. If a feature has more than one incoming or outgoing edge, it is marked as a merge or split event, respectively. However, in the tracking graph, this does not necessarily indicate that an actual merge or split event is occurring. This is because the edges in the tracking graph represent correlations between features. Depending on how these correlations are defined, certain edges may represent what we call a glancing event. We define a glancing event as occurrence where a feature X may have more than one incoming or outgoing edge in the tracking graph at time t, but one or more of these edges is created due to another feature y at t minus 1 or t plus 1. This creates a z-like structure. This figure illustrates a toy example of a glancing event. Each filled circle represents a feature and its correlation radius. The unfilled circles represent the feature's position in the subsequent frame, and the overlap between these are represented by the edges in the tracking graph. I'll note that this structure could also represent one cluster of particles actually passing a particle to another cluster. However, in matching simulation data that I'll talk about towards the end of this talk, we find that this occurs in only 0.2% of these edges that are removed. As a result of this observation, we decided to remove these glancing edges from the tracking graph under this simplification process. So as I mentioned earlier, it's impossible to determine the exact number of particles in a cluster of proteins due to the presence of a dark or unlabeled population. However, it is possible to determine a lower bound on the particle count of a feature by analyzing the tracking graph. Our approach for computing these bounds is straightforward, and this figure gives a visual representation of the process. Each feature at the first time step receives a count of 1. If a merge event is encountered, the counts of the incoming features are added together. These counts are then passed along to the subsequent features. If a split event is encountered, the count of the feature before the split event is distributed among the features after the split event. If we encounter a split event where the number of outgoing edges is greater than the inferred count, we increase the count of the feature at the split event and propagate backwards along the most correlated links. This process happens in conjunction with the creation of time-varying features and is scalable. Ultimately, after the construction of TVFs and computation of the lower bound of the number of particles in each feature, we have an enhanced representation of a feature's existence over time. TVFs can be broken into sets corresponding to the number of particles that the time-varying feature contains, and they can also be processed using their links to other TVFs to analyze how the particle diffusion changes before and after merge and split events. In this manner, our approach enables analyzing how specific protein aggregation and splitting events affect the motion and behavior of these proteins. All these concepts are unified in our interactive visual tool for exploring these SPT datasets. The slide shows the multiple views of our tool. This tool is implemented in Qt and the OpenVisus API. Our tool serves 3 purposes. It enables the visualization and statistical analysis of a given dataset, a task critical to users for validating experiments and gaining an understanding of the properties of features in the dataset, for example, intensity variations. Second, it facilitates filtering of TVFs and the associated visualization and statistical analysis. And finally, it incorporates the analysis techniques I just presented. On the top, we have our tracking graph view. On the bottom left, we have a feature rendering view, which shows all the segmented features at a given time step. In the middle, we have our trajectory view, which shows the TVFs in space. And on the right is a statistics viewer. I'm going to spend a little time talking about A and D. I'll note that the feature rendering view and trajectory views are standard in SPT analysis tools, and we include them in ours because it is immensely helpful to visualize features and trajectories in a spatial context for exploring a dataset. Our tool has a pre-processing step. This step first takes in a segmented dataset that has been linked together to form tracks. Our tool is independent of the segmentation and tracking, although we do incorporate a distance-based tracking method that is used if the tracks aren't specified by the user. The first step for constructing tracking graphs is to first construct metagraphs, which represent all the possible tracking graphs for any user-given correlation threshold for a given data set. For example, in distance-based tracking, this correlation threshold could be the radius around a feature into which to consider correlations for. Once these have been defined, a worker thread is assigned to the tracking graph computation. Starting from a focus time step, the thread outputs tracking graph nodes with edges that have a correlation weight greater than the user-specified threshold. The output alternates around a focus time step every 50 frames to give the user an immediate visualization of the tracking graph without having to wait for the whole graph to be constructed. The tracking graph view is the main component of our system and is linked to all of the view panels so that any user interactions with filtering options cascade through the system, and associated visualizations are updated correspondingly. The ability to filter the tracking graph is a vital component to our analysis pipeline. It serves two purposes: creating statistically meaningful analysis and visualizing targeted data and TVFs. The user can filter TVFs in three ways: by lifetime of the TVF, by the derived particle count, or by a statistical aggregation of individual feature attributes within the TVF. For visualizing the filtered data, the user can select either removing all TVFs from the tracking graph if they are below the specified filtering threshold, or alternatively highlighting the features that exist above the specified threshold. We incorporate a number of options for viewing statistical attributes of the dataset and also time-varying features. So we use mean square displacement as a metric for diffusion, as is a standard in SBT analysis. We provide multiple ways for analyzing the diffusion. The first is a distribution of the diffusion for all TVFs. This uses the trajectories and corresponding diffusion values from the entire lifetime of a TVF. The second way is to perform a similar analysis, but after filtering the trajectories by the number of particles corresponding to that TVF. This filtering is performed by iterating all TVFs and extracting the TVFs that contain the number of particles specified by the user. Finally, the user may create distributions to analyze how the diffusion changes before and after merge and split events. Our data structures make this computation straightforward. We use the linked TVFs and associated diffusion before and after merge and split events and compute the differences. After aggregating these values, the distributional shifts indicate slower or faster speeds with respect to the type of event. To demonstrate our analysis technique, we have applied it to two different experimental conditions aimed at understanding the dependency of KRAS diffusion on the lipid composition of the supporting cell membrane. Before I talk about those experiments, I want to highlight an experiment designed to check the validity of our method. The experiments that are the focus of this paper are part of a larger collaboration between biologists and computer scientists aimed at building a computational framework able to simulate KRAS on a lipid membrane for experimentally relevant time and length scales. We use the results of one of these campaigns, which contains the ground truth tracking for conditions similar to experimental ones. This dataset contains thousands of time steps for 300 RAS proteins. We sampled 100 of these proteins, assumed perfect segmentation, and we used a distance-based tracking method in our tool. We found that the estimated counts are very accurate. For clusters with ground truth cluster sizes 1, 2, 3, and 4, the percentage of incorrect counts are shown on this table. Remember that we removed edges that correspond to glancing events. The incorrect inferred counts are in part the result of removing edges that represent a cluster of particles passing one particle to another cluster. However, because there are so few of these events, the accuracy of our technique is still very high. We performed analysis on two separate real-world datasets produced by our collaborators. The first is with a membrane that only consists of two lipids, which is used as a baseline for comparison. This membrane lacks compounds that are known to possibly induce clustering, so we expect very few merge or split events, and this is reflected in the tracking graph. The primary dataset of interest is the 8-lipid membrane, which is more complex, and we focus on understanding how it affects the clustering dynamics. We can directly see here that in this dataset, it does appear to induce a number of clustering dynamics. For these data sets, we use segmentation method called localizer, which is used by our collaborators. We use the built-in distance-based tracking method and specify the correlation threshold to be 1.5 pixels, which is slightly above the maximal distance the proteins are expected to move in a frame. This slide highlights a key finding from our analysis. The center plot shows a normalized distribution of the MSD values partitioned by the corresponding lower bound count of each track. Whereas traditional analysis gives a general plot like the gray one on the top right, our technique allows us to separate diffusion analysis for tracks with an inferred lower bound count. You can see that there is a distinct separation between these distributions, with particles that have a higher lower bound count having a higher distribution for slower speeds. Not only do we see these distinct modes in the diffusion, but we can also analyze how the diffusion changes before and after merge and split events. This plot shows the distribution of the change in diffusions before and after merge and split events. Negative values in this distribution mean that the feature slows down after one of these events, and a positive value indicates the diffusion sped up after these events. You can clearly see that the diffusion of particles after they merge slows down. Our analysis provides the first direct evidence that diffusion is correlated to the forming or breaking up of clusters. Going forward, the modes of the MSD distribution may provide crucial information on the actual differences in MSD between clusters of different sizes, which would not only provide important insights into KRAS membrane interactions in general, but could also inform the simulation model. I'll emphasize that while our experiments in this work were focused on the KRAS4B protein, the techniques and visualization tool can be extended to general SBT analysis, along with different segmentation and tracking techniques. Despite the success of demonstrating the link between diffusion and clustering, it is important to be cognizant of potential shortfalls. First, our approach is heavily dependent on the quality of both the segmentation and tracking graph construction, and thus failures in either step can skew the results. Also, there will always be uncertainties in the count due to the dark population of unlabeled proteins. One future direction of this work is to better understand the sensitivity to changes in pre-processing, in particular the impact of noise in the segmentation step. Something we're working on right now is how to adapt this method to a new super resolution technique that can distinguish multiple particles within a cluster, in which our method is being used to help validate the technique. As a side note, we've already found that tracking graph structure can be used to remove motion blur effects by removing loops. Finally, this work has the potential to be useful in other application domains. Specifically, it could be used to help define how to track features across merge and split events by changing the cost function for determining most correlated links. Thanks for listening. If you have any questions, I would be happy to answer them.
Okay, thank you, Torin, for this nice presentation. And diving us into proteins in lipid membranes of cells, if I understand correctly. Can you give us a little bit of an insight of how many particle tracts you have in the beginning? Maybe in your there was a 2-lipid and an 8-lipid membrane examples?
Yeah, so generally, so both the data sets that we analyzed contain around 5,000 time steps. And so I don't have an exact number on the number of tracks that we were analyzing, but I would get it's like in the range of thousands.
Mm-hmm.
Yeah.
Mm-hmm. Okay, yeah, there's a nice question from Robin Mack on the slide where you showed the tool overview in the tracking graph A. All features were created or died in the middle time step. What causes such a behavior in the data set? Also on the last slide, he says. I'm not sure if you are able to switch to those slides.
I can pull it up. Let's see. So all features were created or died in the middle time step. Mm-hmm. I think that so part of the visualization and tracking graph is we show the nodes in the tracking graph for like a specific time step. I think that might be what this question might be aiming at, but in general, they either form or die like throughout the entire data set. Yeah.
Mm-hmm. Mm-hmm. Okay. can you, as another question, elaborate a little bit on the difference between the, let's say, biological role of the 2-lipid membrane from the 8-lipid membrane? You 2 examples in the result section, and you said that the behavior is supposed to be different, and you could really confirm that quite nicely. Could you explain a little bit on the context?
Yeah, for sure. And that's definitely not my area of expertise, but I have gotten to learn a lot about it, which has been interesting for sure. And essentially what's happening is in the 8-lipid membrane, there's essentially just more complex reactions happening. We don't necessarily know exactly what those interactions are, but because there's kind of these more differently charged particles, the hypothesis that it does induce clustering, and that is indeed what we saw in the tracking graphs.
Pretty nice. I'm sure you're looking forward to continue to cooperate with the Frederick Natural Laboratory, because cancer is one of the big threats, even that everyone just forgot about it because of the coronavirus. But anyway, I see no further question, and time is passing. So we thank you once again. Very nice presentation, Torin. Great work. And I encourage everyone to continue the discussion on Discord. I'm sure Torin will be around to answer your questions there if we continue. And we are now switching to our third talk of Tabassum.
Thank you.
Yeah, welcome again to the Medical Applications in GPU session. Our next speaker is Tabassum Kakar from the Worcester Polytechnic Institute, and she will take us now really into the classical medical domain. It will be about incident reports and how visualization can support the FDA, the well-known Food and Drug Association, in processing these reports to help prevent further medical incidents and so on. Of course, Tabassum can explain this much nicer. This is work together with Kin, La, Suhu, D, Rundensteiner, and Harrison. They are mostly at the Rochester Polytechnic Institute, but some are at the FDA. The talk is called SumRe, Design and Evaluation of a GIST-based summary visualization for incident reports, Triage. And Tabassum, I leave the stage to you. It's your talk now. We're all looking forward.
This is Tabassum Kakar from Worcester Polytechnic Institute, Massachusetts. Today, I'll be presenting our paper summary on the design and evaluation of a GIST-based visual summary for incident reports triage. Before diving in, let's understand what are incident reports. These are complaints or reports submitted about issues related to products and services to regulatory authorities for them to take action. For instance, service difficulty reports related to aircraft health and safety are submitted to the Federal Aviation Administration. Similarly, one of the responsibilities of the Consumer Financial Protection Bureau is to investigate fraudulent transactions through financial fraud reports. In the healthcare domain, regulatory authorities such as the US Food and Drug Administration receives and analyzes drug safety reports related to medication errors and adverse drug reactions. One thing across all these incident reports is that it involves data-driven critical decisions that involve human judgment. Our focus in this work is drug safety reports, which was done through a collaboration with the FDA to design visual analytics for supporting their drug safety incident reports workflow. To understand what drug safety incident reports are, imagine a patient, Alex, who is suffering from diabetes and her physician prescribes her Avendia to help with the diabetes. After taking the medication, she has a heart attack, and that's considered a side effect of the drug Avendia. The physician submits a report to the FDA, and similar reports are submitted across the globe to regulatory authorities. And timely detection of such incidents, such as adverse reactions or medication errors, can save thousands of lives and billions of dollars. This is an example of an incident report submitted to the FDA. It has information related to the patient, drug, the reaction that happened, etc. In short, if we look at the report, it has some structured information and also a text narrative that gives the description of the incident that happened to the person. Now, analysts at the FDA perform a detailed analysis of these drug safety reports to identify safety issues. Basically, the analysis involves triage and investigation, and once an incident is confirmed, then regulatory action is taken, such as adding warnings to the drug label. Our focus in this work is only on the incident reports triage, and we do not address the investigation of these reports in this work. To understand incident reports triage, basically analysts review these reports using looking at the structured information, and for each report they make a decision whether they should investigate the report further or no, which is a lengthy and complex process. Now, in the tabular layout, each row represents a report, the structured information in a report, and analysts need to scroll through the table to get the gist of the whole report. And using this tabular layout can be error prone and cognitively demanding, and we see an opportunity for our visual design. So our research questions in this work are that how can we design a gist-based visual summary that can help analysts in the triage, and to what extent would such visual summaries be efficient or effective in triage? So to understand, our first task was to understand how exactly these reports are triaged at the FDA, and for that we conducted interviews with six drug safety analysts, and our goal was twofold. First, we wanted to understand the information that's important for triage, and second, we wanted to know how is this information analyzed during triage. So related to the first part of the question, through our interviews, we understood that analysts look at certain information during triage. This includes information related to patients, such as the age, gender, the medications that they are taking, information related to the incident, such as which drug they took, when did they take the drug, and then events that happen after the incident, such as whether the person was hospitalized or no, what treatment was given, etc. The second part of our interview was to understand how are these incidents analyzed during triage. So we understood from the drug safety analysts that they form looking at certain information, they first form a hypothesis about the incident to see whether the incident is serious or plausible. We call these data attributes primary triage cues. They include such as if the incident resulted in a serious outcome, such as a death or hospitalization, and if the reaction is a severe reaction. These primary triage cues are low cardinality attributes, which means they have one or two categories. Once analysts form a hypothesis looking at the primary triage cues, then they look for other information to see if their hypothesis is rejected or the information support their hypothesis, we call these data attributes secondary triage cues. Such as these attributes include medical history or the other drugs that are taken by the patient, to see basically that helps them to see if there is an alternate explanation for the incident or the adverse reaction. One thing to note about the secondary triage cues are that they are high cardinality attributes, which means there are like thousands of drugs that are possible or out there, and similarly hundreds of adverse reactions are possible with a particular drug. So to design a gist-based visual summary, we set a set of design goals or guidelines. For instance, our goal was to present a compact view of the whole report or all the triage cues that can help them get the gist of the report easily. Second, as we have seen, the triage cues have certain categories, so supporting or facilitating the analyst to differentiate among different triage cues, that's also one of our goals. Third, because they need to make decision for each individual report, so we wanted to facilitate the analyst in a way where they can capture their insights about a certain report and also the triage action. Based on these design guidelines, we designed SumRe. So this is our visual summary, and it's equivalent to one row of the table representing a single report. If you look at our design, on the left hand side we have patient information. We call it the profile panel. The patient information is followed by incident related information, which includes the drugs taken, the adverse reaction, treatment that was given, and that's followed by the triage, the analysis panel, which helps analysts capture their triage artifacts, including what action they took or any insights that they have about a certain report. To identify the primary triage cues, we design world scale icons. Just to review, the primary triage cues were to present information about the plausibility or seriousness of the incident. So we designed these icons for each of the triage cue. For the secondary triage cues, we use special alignment and color encodings to differentiate between them. For instance, the patient information is on the leftmost, and it's followed by the incident related information. If you look at the existing work for document summarization, a majority of the work fall under the exploration category for document corpus, which includes a set of documents. For a single document, we see some visual summaries, but they are designed for books or research papers, which are different than incident reports. Similarly, for triage, we see at a corpus level or a document set level, there is some work done for visualizing email data using network diagrams. For single documents, we can say that we have seen some work on designing web page previews. This is very similar to the work that we are doing, and one can imagine the search results that are returned by Google that represent a visual summary of each web page. However, again, because the type of documents are different and incident reports are more specific, so we look at some of the work that's done for visualizing incident reports. We see that a set of documents are visualized using node link diagrams or a tree map, looking at the existing work. Our contribution through this work is visually representing a single report by designing a visual summary of these documents. Our next task was to evaluate how effective a visual summary is for triage. So we conducted a crowdsourced study to compare two layouts. One is our visual layout summary, and the second one is a tabular layout that's currently used at the FDA for triage. The study was set up with the study was conducted within subjects with 20 domain experts. Our data included 2 report sets. In each set, half of the reports were indicative of investigation, while other half were not. And the main task was we asked the participants to pretend to be drug safety analysts and were given a set of drugs, a set of reports to triage. Triage actually included asking them to take to review the report and make a decision whether the report needed investigation or no. We also asked participants to perform low-level tasks, including information search, extraction, and comprehension. Triage task was followed by a recall task where we presented some of the reports from the triage task, and we presented blurred images of these reports for each condition and asked the participants to recall as much information as possible. Our study results show that participants were able to correctly identify reports that were indicative of investigation, which is also known as precision. Similarly, participants were able to make more serendipitous discoveries with the visual layout as compared to the table, although this result is not significant, but it is an important aspect because practically a drug safety analyst may come across reports that are unrelated to the drugs that they are assigned to. However, reporting on such reports is still very crucial for the drug safety workflow to identify any safety issues. For the questions related to information extraction and comprehension, we see that participants were able to extract this information more accurately and in a timely fashion with the visual layout as compared to the tabular layout. For the recall task, we see that more participants were able to recall information with the visual layout as compared to the table. And the majority of this information was coming through the primary triage queues as compared to the secondary triage queues because primary cues were visually encoded and they were able to identify and remember that. We also asked participants to report their preference for using a certain layout if they were to analyze these reports on a regular basis. As you can see, majority of the participants prefer to use the visual layout, and the reasons that they provided for using for their preference or using the visual layout included that that the visual layout is faster, engaging, appealing, accurate, easier to use, and also enjoyable. During the study, we also asked participants to freely explore the reports and report any insights. We analyzed these insights through qualitative coding. Looking at these insights, so we call an insight guided if it's based on the study material, the training material, or anything that was covered in the questions or tasks. And an unexpected insight is the one that's not covered in the study. And you can see that with the visual layout, a high number of unexpected insights were reported as compared to the table, and the opposite is true with the guided. Similarly, we call an insight a report level insight if it includes more than one data attribute or more than one triage queue in the report, and an attribute level insight is the one that includes only one attribute or a triage queue. And you can see that participants were able to make more report level insights with the visual layout and more attribute level insights with the table layout. The reason for that is because the visual layout is more gist-based, so they can see multiple attributes at once, and they could observe interesting insights about the report, as compared to the table where they had to scroll through, and the majority of their insights were related to a column, which is basically one attribute or one triage queue across multiple reports. Also, we observed that majority of the insights provided with the table layout included the missing information. This is because the table did not have any other visual encoding except for the missing information. So participants were more focused on that visual encoding or the missing information. While with the SumRe, we saw that because of other visual encodings, participants were able to report on other insights besides missing information. Looking at the total number of distinct insights, we see that participants reported on a high number of insights with the visual layout as compared to the table. With each task, we also asked participants to rate their confidence and ease in performing that task with each layout, and we see significant differences in these perceived confidence and ease with both layouts, where participants found it more easier, found the visual layout more easier to perform the tasks. To conclude, we can say that a visual summary can lead to accurately get the gist of the report in a timely manner, and also help in making serendipitous discoveries and identifying reports that were indicative of investigation. And overall, a visual summary resulted in a better triage experience and engagement. For future, we are interested to explore the addition of interactions with the visual summary. Currently, we only provide the hover over interaction where participants were able to get the details of our triage queue, but other interactions such as sorting and grouping can be studied to see how it shapes the triage experience. Similarly, adding the visual summary along with the text narrative that's provided with the incident, studying them together to see how that will impact the reading behavior or the triage experience itself would be an interesting direction to pursue. Thank you for listening.
Hello again, and hello to Tabassum, our very nice speaker. Thank you for your talk. There's already one question from the audience, from Robin Mack. Do you plan for a comparison tool using your summarization with to examine reports containing the same or similar drug together? This might help to find a cause of a reaction to a drug much faster when there are multiple cases at the same time. So some comparison of different reports.
So currently the way we conducted our, hi everyone, thank you for the question. It seems a very good question. So currently the way we are conducting our study is we are providing a set of reports related to one drug. For instance, we had Avendia in one set and then another set which was given to the same participants but with another layout. It also contained like 6 reports about the same drug. So that was the goal, because actually in the workflow with the FDA, they filter the reports, for instance, for a same drug or same reaction. So that's usually a bunch of reports, but they pay attention to each report individually. Yeah. So this is something we actually did in the current study. If I understood the question correctly, if not, please correct me.
Yeah, no. When there are some open issues, just continue to put something in the Discord channel. By the way, if I understand your system correctly, you start basically with some table, like an Excel table, where all this information from the report is put in. Have you thought or other ideas also to use some kind of text processing to analyze these sections where there is kind of continuous text? There is some very structured information, of course, this is easy to process, but there's also some free text information. Is there some idea on checking them if they have thousands of such reports? Of course, they have to look at all of them, but sometimes you know, you want to have a quick overview. Like the COVID vaccine, there may be thousands of reports coming in every day that could overwhelm them at some point. So are there ideas in this direction?
So that's actually what they are doing.
Okay.
So with every report with this structured information, there is unstructured text.
Mm-hmm.
But the goal of this whole triage was that looking at the structured information very quickly, they need to decide whether they should look into the narrative or no, because narratives can be very long. So the whole goal is, the first step of investigation is whether they should read the narrative or no.
Mm-hmm.
And then once they are reading the narrative, then it's another whole class of investigation where they have to find similar reports, and there's another system that we are working on for that to continue with the text investigation.
Yeah, because I was thinking that NLP, natural language processing methods, right, could help looking at the narratives immediately and look for signaling words and things like that. Okay, but if you're working on that, that's nice. There's another thing. When I was looking at your study, right, I was a little bit afraid when I saw that the accuracy and also the finding out of this serendipity analysis, where you try to figure out some problem that's not directly associated with the track which is in focus right now, that these values with the classical methods were quite low. Yeah, the accuracy was kind of 50% or lower, and with the serendipity, they were missing, what was that, 2 out of 7 cases in your examples. Was that due to the way you conducted the study, because the participants are not all experts doing that for the FDA, or is there really some kind of a problem that they hope to not come across if they actually do their work? Because I was shocked to say, well, if the accuracy is kind of 50% only, that's much lower than I hope that they are working on, right?
Yeah, so this one is, so you are talking, so just to rephrase what you said is looking at the precision. So the accuracy was pretty good. Accuracy was around 98% or something, like it was very similar for the both layouts. There wasn't much difference. So the first thing that we are talking about is precision. It's basically the 4 reports which were signaling towards investigation, and can they find that within that using both layouts, right? So your question is, if that's true, then it's not something good for the FDA because they are not doing a good job with the table. So one thing is, it could be because although our participants were experts, kind of like they're medical students, retired doctors, but they were not very used to the FDA workflow or the safety reports. Some of them were, they knew the reporting and everything, but not all of them. And the FDA analysts, they are more, because they are doing it on a regular basis. And plus they have, so one is this, so there are 2 kind of reviews that they do. One is this regular influx of report that they have to do every day. And then there are specific reviews, like if there is an issue someone else highlighted or it's coming from outside, then they have to investigate and find out it. So the chance of error is both, like it's possible with the visual layout and the tabular both. But I think with the visual, it's just, it highlights the critical information. So even false positives cannot go missing. So if even something is severe, for instance, interesting case is people with some analyst who is reviewing drugs for old people, majority of them end up in hospitalization or they die, but it's not because of the drug, it's just another factor of age, but because they have experience in this and they can relate it very easily. The second part was the serendipitous discoveries. And that's, we just gave 2 reports. So my understanding is why we gave a smaller set of reports as compared to having more. So we already had 8 reports in our set, and it was so each participant were going through 16 reports. So it was already from our pilots, we understood some people were feeling like fatigued, like they were saying it's a long study.
Okay.
So just to keep it moderate and something that can give us a good results of it based on that. And
okay.
a similar thing was done in a network alarm kind of like investigation, where they were giving one unrelated alarm, and they just wanted to know if participants can observe it or no. So it was something following a similar strategy.
Yeah, thank you for also this very extensive and informative answer. Since there are no further questions and the time for the streaming session is over, I encourage everyone to continue the discussion on the Discord channel. I'm sure Tabassum and also the other speakers like Yifan and Torin are around to answer your questions. Of course, no one is preventing you from discussing to each other regarding the audience. At this point, I'm going to close the session, but first of all, I want to thank Yifan, Torin, and Tabassum for their very nice work, for their very nice presentations, also for answering all the questions, sometimes even rephrasing my questions so that the audience gets a clearer view. I also thank Marina Evans, our student volunteer, and the technicians in the back. You haven't noticed them, which means they did a great job, but they definitely earned an applause. So thank you from my side to everyone. And once again, this is not over. You are welcome to continue on Discord. Thanks again. Goodbye.